Swayam Prabha. Digital India. Educated India.
Good morning. So now we will delve into a new kind of separation process as known as liquid extraction. But from a chemical engineering point of view, liquid extraction basically means separating it's a separation process of a constituent of a solution by introducing another liquid which is insoluble with the original liquid. Okay. In a way, this definition is very similar to absorption and desorption, but in absorption desorption, the two phases are liquid and vapor. But in liquid extraction, both are liquids, but they are insoluble. Okay. Otherwise, conceptually, they are very similar. Okay. So we like to say that liquid extraction, aka also known as solvent extraction. Okay, so this is it's a separation process of the constituents of a liquid solution by contact with another insoluble liquid. So this insoluble nature of the liquid is very important because we need to separate them anyway. And so how is it possible and why is it possible is because between the original solution and the added insoluble liquid, the components are differently distributed. Okay, so that's why the separation is possible. So we say that this separation is liquid extraction is possible because the solute is distributed differently. When I say differently, I mean the mole fractions are different between the original solution and the new solvent that we add. Okay, so this is a very characteristic feature of a liquid extraction or solvent extraction. This point can be illustrated with an example, very simple example. This is something that we discussed in the very beginning of the course. So you could think about having a solution of acetic acid and water. So acetic acid and water, these are soluble mixtures. Okay, it's a single phase. So what choices we have if I want to separate this acetic acid from water? What choices we have? Okay. So basically, what we are saying is acetic acid and water. In principle, we can use distillation because their boiling points are quite different, and but economically speaking, distillation may not be the right way to do because the separation factor, that is the relative volatility, is not very high. So you have to design a very large column to enhance separation, so on. So economical point of view, distillation is not possible. But the point is that there are other methods too. Okay, so liquid extraction is not the only method. There are other methods too to separate. So there are other considerations: cost, spatial requirement, and then environmental friendliness of the operation, etc., etc. There are so many things that we have to deal with. But let's say we will take acetic acid and water, where other methods of separations are also possible. Okay, despite that, let's say we want to use extraction as a principle to separate acetic acid from water. So what we would like to do is we would like to add a solvent, something like ethyl acetate. Okay, it's an ester, and it is such that this ethyl acetate and water, these are not miscible with each other. I mean, they are miscible at certain compositions, but broadly, when the compositions are nearly pure form, they are not miscible. So they basically feel phase separate. Okay. So we add ethyl acetate and then we stir, so that there is a good contact between the aqueous system and the ester system. Okay. So we stir for some time and then we allow it to settle. Okay. So there is some amount of given time is given for mixing, and then we basically let it settle. And then what you will find is that after this operation is over, you will have two layers. The upper layer we call this as a ester layer. So this is basically rich in ethyl acetate, and this will also have little bit of water, because water will have a very small solubility. Okay, very little amount of water may be present in the ester layer, and acetic acid will also be present. And if you look at the bottom layer, this is actually water layer or water rich layer, and here you may say very little amount of ethyl acetate also, but in a very minute quantity, and then there will be also acetic acid. Now, if you look at the compositions of acetic acid between all these three things, the original solution, the ester layer and the water layer, the way that the acetic acid is distributed is going to be very different. Okay. For example, let us say that XF is the mole fraction of acetic acid in the original solution. Okay. And let us say in the ester layer you have a composition. I am using a different letter here, YE. I will come to that what it means. Let us say the mole fraction of acetic acid in ester layer as YE, and then the acetic acid in water rich layer as XR. Okay. So XF, this is a mole fraction or weight fraction, maybe let us use weight fraction, does not matter, weight fraction of acetic acid in the original solution. So this is before we add the ethyl acetate, and we say this YE is the weight fraction of acetic acid in the ester rich layer, and XR is the weight fraction of acetic acid in the water rich layer. Extraction of this kind is possible only if we have a situation where YE is much larger than XF and that is less than XR. So, starting with XF as the weight fraction, by adding ethyl acetate, we have reached a ester layer in which the composition of acetic acid is much higher than what was there in the original solution. So, there is some level of separation is then possible. Okay. Suppose if YE is almost same as XR, what it means is that the acetic acid weight fraction in the ester layer and water layer, if they are very similar, then we have not really achieved any separation. Okay. But we are taking advantage of the fact that acetic acid likes to be in ester layer in far more quantity than in water is the guiding principle in liquid-liquid extraction. So, that means we need to find a solvent or the added insoluble liquid such a way that the solute likes to be in that solvent in much more quantity than in the original solution. So, that is a choice we have to make, and we have a choice, unlike in distillation where the vapor phase is created from the liquid phase itself, where we do not have much of a choice in changing the chemical nature of the gas. But here in liquid-liquid extraction, like in absorption and desorption, we add a phase, we add a new phase, and we have a choice to choose that phase, and we choose such a way that the solute can be distributed in larger quantities. Okay. So, selection of a solvent for liquid-liquid extraction is a one big decision making process. Now, if you want to continue this operation, so this operation is a single stage operation. We take a feed we add a solvent or a insoluble liquid, and then we stir it, let it settle, and then we separate the two phases, the ester rich and water rich. So this constitutes one stage or single stage operation. Now if you want to continue this further, what you could do, you can take this water rich ester lean acetic acid solution and then do over one more round. You take this water rich layer, to this you add another set of quantities of ethyl acetate and do over. So that basically leads us to multi-stage operations. At every stage we will be able to recover acetic acid continuously. Okay, so we are saying that in a multi-stage operation, we can probably remove pretty much everything, every acetic acid present in the original solutions over multiple range. In single stage you may not be able to get everything, but over multiple stage you can get as much acetic acid as possible. Okay, so at this point I would like to introduce some terminologies specifically used in extraction. So feed, for example. Okay, so we say something as feed. This is the original solution. The original solution containing solute C in solvent A. So now I am using some letter here to denote the solute. I use the letter C and the solvent in the original solution as letter A. Then we have solvent. This is a solvent, this is the insoluble liquid that we add, the insoluble foreign substance that we add. We can call this as B, component B. So essentially the minimum number of components involved in liquid-liquid extraction is 3. There is a solute C in its solvent A, and then additional solvent B is added. Okay, we will pretty much consistently use this kind of terminology: C for the solute, A for the original solvent, B for the insoluble foreign solvent added. Now we since this operation leads to two phase separated liquids, we have what is called this extract. So this extract is basically the solvent rich, solvent B rich phase. So the liquid that is rich in solvent B, we call it as an extract. And raffinate, R-A-F-F-I-N-A-T-E, raffinate. So this is basically the residual liquid from which solute C has been removed. So if I have to make connection to these terminologies to the example I showed you here, we would say the feed here is nothing but acetic acid plus water. Okay, so this is our feed. Acetic acid is component C, water is component A, and solvent is the ethyl acetate, which is component B. Extract. So extract is basically the ethyl acetate rich layer. Raffinate, this is water rich layer. And a small note about applications of liquid extraction. So generally liquid extraction is a competitive process to distillation. Okay, it's used as an alternative to distillation. So more specifically, if you have a solute that is thermally sensitive, that you don't want to cycle them through vaporization and condensation, and you expect that the solute may degrade or decompose, and you don't want to involve heat application, then you can say that for thermally sensitive products, we could use liquid extraction. And secondly, sometimes when you have a very dilute aqueous solution and you want to separate the solute from this large amount of water, we don't prefer distillation because we may have to add a lot of heat to vaporize water, because water is in large quantity, latent heat of water is very high, so sensible heat is also quite high. So we want to avoid that. So in such case, liquid extraction is also a potential competing process. Sometimes liquid extraction is also used to replace some of the chemical process. This is alternative to chemical process. So this involves, for example, metal separations, metal ore separation, and inorganic chemicals like phosphoric acid, boric acid. So there are in the synthesis of many of this inorganic chemical species, phosphoric acid, boric acid, one could use liquid extraction as a potential alternative to chemical driven process. There are the third approach where sometimes there is no separation available. When there is no separation available and we see that liquid extraction is the only possible separation out there, okay, is the only viable separation. For example, I think in the case of aromatic and paraffinic hydrocarbons, the vapor pressure of these aromatic and paraffinic hydrocarbons are very similar, that distillation is not really a possible operation. So we could use a solvent extraction or liquid extraction by choosing a solvent that will selectively solubilize either aromatic or paraffinic. Okay, so that's one possibility. And another bigger area in which extraction is used is pharmaceutical. In pharmaceutical compounds, which are active products, extracting active products without denaturing them, without decomposing them in an active form, liquid extraction is very much used, including penicillin separation from its original solutions. So pharmaceutical is a big area for including penicillin separation. So the fact that liquid extraction is alternative to distillation, chemical processes, and other processes in which only liquid extraction is possible, the fact that this liquid extraction has to be dealt as an independent individual separation process, and then we need to look at various separation process principles for extractions. So one of the an important thing about liquid extraction is that I said there are three components involved minimum, and the two liquids, even though we say insoluble, but still there is some amount of the solvent is present in both ways. Okay, for example, in the acetic acid water system, I said even though the ester is rich in the top layer, it also will have some amount of water, and similarly the water rich layer will have some amount of the ethyl acetate also. So that means that we need, whenever we talk about liquid extraction, we have to think about equilibrium data connecting all the three components in two phases. Okay, so in one angle in which this liquid extraction is quite different from other separation is how we display the equilibrium data. Okay, so we use what is called this triangular diagram to denote a liquid composition containing three components. okay, because it involves three components. So let me show you an example of a diagram. So generally we have you seen this kind of a ternary diagram before? No? Okay. In thermodynamics? Okay, no problem. So here if you see it's basically an equilateral triangle, okay, all the bases are of equal length, and so we have this apex, three apex and three baselines, and you can also see that I have noted each apex with a letter, and I already said component C is the solute, component A is the solvent of the original solution, and component B is the foreign substance that is added as a solvent, such that A and B are insoluble. But before we talk about solubility in two-phase, imagine that in this case, let's say all A, B, C in all composition form a single phase. Okay, we are talking about an example here. Later on, I'll talk to a two-phase system later on. So now suppose you have A, B, C is a three-component system. And single phase. And we use a equilateral triangle to depict the composition of a ternary mixture. And we say that each apex is a pure species. That means that if I take a point here, that means 100% pure C, which is a pure component of C. And if I take this apex, this means it's a pure component of A. And this point here is the pure component of B, right? Now each base is a binary component, is a binary mixture. Okay, suppose if I take AB, the line base AB here, any point along the base AB is a binary mixture of A plus B. There is no C present at all. It's a binary mixture of component A and component B only. And if I take AC, this is a binary mixture of A and C only. No B present along this baseline here. Any point along this base contains only A and C. Similarly, BC is a binary mixture of B and C. So we are saying that in this equilateral triangular diagram, all the apex correspond to pure species, and all the bases are corresponding to binary mixture based on which apex they connect. Here, this line AB connects apex A and B, so it is a AB base, and this line connects A and C, so that is a AB baseline, and this particular baseline connects apex C and B, so we say it is a base BC. All these baselines are binary components only. The third component is missing there. So we covered the base, we covered the apex. The only thing that is left is the interior part of this diagram. So if you take any point inside the diagram, it would mean ternary three component system where all the species are present in finite quantities. So now the important thing is to if I tell you a three component composition, we should know how to denote that point in this diagram, or conversely, if I tell you one particular point in this diagram, we should know what the composition of this. In fact, there is a gate question given a point in this ternary diagram, finding out what is the composition. Okay, so we should know how to read composition in a ternary diagram. Okay, so to illustrate that, I have taken point K here. This is point K, And so all this gray line that you see that is going crisscrossing, this is just a baseline. Okay, so they don't mean anything here at this point of time. This is only for our reference. Now, one more thing before I go to point K, also let me tell you how we have graded this basis. So I said this is component B, and the way we have done is along the line AB baseline, here A is 0, here A is 20%, here A is 40%, 60%, 80% and 100%. Because in the line AB, only A and B are present, we reach from 0 to 100% A. Similarly, if I take line AC, here component C is 0 because it's B, A is 100%, so C is 0 here, C is 20% here, C is 40%, 60%, 80% and going to 100%. So it is basically a linear scale. Similarly, along the line BC, we know that this is 100% C, that means B is 0 and here B is 20%, B is 40%, 60%, 100%. So you can see that I have put an arrow here to denote how each component is actually increasing from 0 to 100 in each of those baselines. Okay, so here A is increasing from 0 to 100, here C is going from 0 to 100, here B is going from 0 to 100. Okay, so this is important to know before we finding out the composition of this point K. So let's say we have point K and we want to know what is the percentage of A, B, C corresponding to point K. Okay, so I already said that this line AB is where C is 0 and here C is 100. So the way we do that is I take a ruler. Okay, I take the ruler here and first what we will do, we will find what is the composition of C at point K. So what I do is I know that the line AB corresponds to 0% of C. Okay, so I move this ruler such that it is parallel to the baseline and then go all the way to K. Okay, so from baseline AB, I move this ruler such a way that it is parallel to line AB, and then I know that on the left hand side, I know that C is going from 0 to 100. So then I read the amount of C is 40%. Okay, at point K, amount of C is 40%. So point K means 40% C. So now let's find out what is A. So for A, I am going to go to this baseline because I know this baseline corresponds to A equal to 0 and this is A equal to 100%. So I move this ruler parallelly and then reach this point K here, and where the axis for A increment, the baseline AB. So A is 0 here and I move and then come this point and I read this point as the amount of A present corresponding to point K. So this also is 40% A. Now you can directly write B will be 20% because the sum of the composition should be 100%, but you can also read from the graph that B is 100%, B is 0 along the AC. So I am going to move this line like this. So this is line AC where B is 0 and I move this ruler to point K, okay, and B is incrementing along this line. Okay, so this line K cuts the point somewhere here, so I know it is 20% B. So that's what we have mentioned here. So here we have given a point and then asked what is the composition of the this particular point. Conversely, I could give a particular composition and then we find out where the point is. Okay, so this is a method by which you can calculate the composition of a given point. Is it clear? Okay, so all we need to do is that we go to a place where the component is 0 and then move parallel to the line to the point of intersection and then read the corresponding percentage in the respective axes. Okay, like I said, you should know where C is increasing, where B is increasing, where A is increasing, so as to read. Sometimes we reverse this axis. Sometimes we say we write in terms of B in this line. Okay, so whichever way it is given, we should basically approach this particular method. Now, if you look at point D, what would you say about point D? So point D is in the line AB. So what is the amount of C at point D? 0, because it is corresponding to the baseline AB where C is 0. What about percentage of A at point D? It's 80%, very good, and B is 20%. Okay, so here I have also drawn a line here, the purple line connecting point D and point C. So at point D, C is 0. At this apex, it's a single component having 100% of C. It's a pure species. Anywhere between these 2 points, if I take a point along this line, you will see the ratio of A to B is fixed. Even though A, B, C, these are all changing along the line, the characteristic of this line is that the ratio of A to B will be fixed. Okay, so these are the 3-4 important things you should remember. In a triangular diagram of a single phase system, the apex are pure components, bases are corresponding binary mixtures. Any point inside the diagram would be a ternary composition. Now, what we are going to do next is to take 2 composition inside the diagram and mix it, and then find out where would be the mixture composition be. Again, we are talking about a single phase. So this basically takes us to a material balance, application of material balance. Again, let us illustrate with an example here. So you can see that this is a slightly neater version of the ternary diagram. You can see that the apex are ABCs, and all the grid lines are now taken away, and we understand that C is increasing this way, B is increasing this way, and A is increasing this way. And so let's say that you have a solution corresponding to point R. R will correspond to particular composition of ABC. Okay, so we say okay, so we will come back to that now. So then now take another solution corresponding to E. So you got 2 solutions, one corresponding to composition at R, another solution corresponding to composition E. Okay, take some amount of each and then mix it together. When you are asking, once I mix it, again in this case I am talking about a single phase system, what would be the final mixture composition? So that's a question we would like to answer. Okay, and this can be done very similar to how we used 2-phase mixture, Liver rule, applying total material balance and species balance. So let us show that this point M will correspond to the mixture composition. Okay, and where the location of M will be depends on how much amount of the solution at R and how much solution of at E I am mixing. Okay, so let us do this by mass balance space. So let's say I add R kg of solution at composition R. Okay, I am using this letter R to denote both mass of the solution but also the point of the corresponding composition. Let us say I have another solution, that is E kg of solution at composition E. In both R and E, we have A, B, C at finite concentration, because both points in R and E are inside the triangular diagram. So the question we would like to ask is, where do we locate the mixture composition? So what would be the total amount of the solution after mixing? R plus C. Okay, so that is anyway straightforward. So total balance we can do, the mixture at point M will have this. Okay, the amount of liquid at composition M will be just R plus C. Okay, so here everything is in kilograms. Now what we will do is, you see that I have also noted XR, XM, XE to denote the percentage of component C in those solutions. Okay, XR, this is the weight fraction of C in R, in the liquid R, and Xe, this is the weight fraction of C in the liquid E, and Xm, this is the weight fraction of C at the mixture composition corresponding to. So, because this total material balance has to follow, similarly the amount of C should also balance out after mixing. Okay. So, we basically take R kilogram of composition XR. So, this will be the amount of C present in R plus E times Xe, this is the amount of solute C present in the solution E, and this must be equal to M times Xm. Okay, so this is basically species C balance. So we know that this M here is not an independent quantity, but this is basically R plus E. So basically I am eliminating M, we are basically eliminating M as R plus E. So so remember this R by E, this is the relative ratio of R to E. Okay, how much kilogram of R, how much kilogram of E, that is basically something that we decide. We know how much we are adding. Okay, and that ratio is actually given by Xe minus Xm by Xm minus Xr. So this is coming purely from a material balance point of view. So from this diagram point of view, what does this Xe minus Xm mean? Okay, Xm minus Xe. So Xm is here, R by E, this basically is line EP by line PS. So what is EP and PS? So you can see this Xe minus Xm is nothing but less line EP, and Xm minus Xr is nothing but line PS. So these are the vertical line EP and PS. And if you want to write this further down, you can also say this is nothing but line ME by line RM. So the way I have written is that if you look at this length line line EP, and this line EP can be written as some sine theta times line ME, that triangle, and since this angle is also same, line PS can be written as some sine theta times line RM. So those angles will cancel. So you can show that the ratio of EP to PS is nothing but the ratio of ME to line RM. Okay. So if I know what is R, what is E, that ratio will tell me where the location of M will be. Okay. Suppose if I have very large amount of R, so let's say we have R is in much larger quantity than E. So we know that R by E, this is much larger than 1. So this means line ME is much larger than line RM. So this means the point M is closer to R. okay, because this line ME is much larger than MR, so the M is coming more closer to R. Similarly, if I have the other way around, that I have R is much lesser than E, so then I have R by E is much less than 1, so that means this line ME by line RM is much less than 1. It means the point M is closer to E. Again, there is nothing magic here, it's all coming right from the material balance point of view. Okay, so the point of doing this exercise is that if I have a ternary mixture, two solutions of a ternary mixture, and if I mix it, what would be the final composition? Okay, so that is the point of making here. Okay, so subsequent, so whatever we have done is based on a single phase composition, but actually in liquid extraction, the basic principle is that the two liquids have to be insoluble. Okay, so you're going to be having binary mixture, you're going to have ternary mixture in two phases. Okay, so that is the point of next class, where I will take this ternary diagram and show a demarcation between a single phase and a two phase, and then dealing with mixing, you know, two binary liquids going through the miscibility boundary, and then see how the principle of liquid extraction is employed here. Okay, so we'll stop it here.